Earth satellites. Its Earth satellites are orbit which revolve around the Earth. Orbital velocity. This is Earth, and this is the satellite which is orbiting around the Earth. The radius of Earth is RE and mass of Earth is ME, and the mass of satellite is M. That satellite is revolving in circular orbit at height h from Earth's surface. The orbital radius of satellite is r equals to re plus h. The centripetal force required to revolve the satellite in orbit is provided by the gravitational force on satellite. The centripetal force equals to gravitational force. This implies mv square by re plus h equals to gme m by re plus h का whole square. This gives v equal to under root gme by re plus h the whole square. Question 1. If g be the acceleration due to gravity on the surface of Earth, then g equal to gme by re square. This implies gme equals to g into re square. Using this in equation 1, we have v equals to under root g re square by re plus h का whole square. Equation 2. When satellite revolves close to the Earth's surface, then h is very less than r, and r plus h equivalent to r. Hence, v equals to under root g re square by re equals to under root g re. Putting all values, that is the value of g as 9.81 and re as 6.4 into 10 to the power 6, we get 7.92 kilometer per second equivalent to 8 kilometer per second. That is orbital velocity of the satellite very near to the Earth's surface is about 8 kilometer per second. Now time period of revolution t. It is time taken by a satellite to complete one revolution. To complete one revolution around the Earth, it is given by t equals to circumference of the orbit divided by orbital velocity equals to 2 pi into re plus h divided by g. 2 pi re plus h under root gme by re plus h. This implies t equals to 2 pi re plus h to the power 3 by 2 under root 2 gme equals to 2 pi re plus h to the power 3 by 2 under root g re square equals to 2 pi root under root re plus h by g re square. Squaring both sides, we get t square equals to 4 pi r square gme re plus h का whole cube. This implies t square equals to k into re plus h to the power cube, where k equals to 4 pi square by gme, where k is a constant, and this implies t square proportional to re plus h to the power cube, which is the Kepler's law of period. For a satellite very close to the Earth, h can be neglected in comparison to re, that is radius of Earth. Hence, time period of the satellite near to Earth's surface t naught equals to 2 pi re to the power 3 by 2 under root gme. 2 pi re to the power 3 by 2 under root g re square equals to 2 pi re to the power 3 by 2 under root g into re, since gm equals to g into re square. This so it equals to 2 pi under root g into re to the power 3 by 2 minus 1, 2 pi under root g re to the power 3 minus 2 by 2, 2 pi under root g re to the power 1 by 2, or equals to 2 pi root under root re by g. Hence t or time period of revolution 2 pi root under root re by g. Substituting pi equals to 3.14, re equals to 6400 kilometer, and g equals to 9.8 meter per second. In equation 5, we get t0 equivalent to 85 minutes. Energy of an orbiting satellite. First, kinetic energy. The kinetic energy of a satellite due to its orbital motion is K equals to 1 by 2 mv square equals to 1 by 2 m under root g me by re plus h to the whole square equals to me g me by re plus h equals to 2 g me into m by 2 into re plus h. Second, potential energy. The gravitational potential energy of the satellite is given by potential energy equals to minus g me m by re plus h. Total mechanical energy of the satellite E equals to kinetic energy plus potential energy equals G me m by 2 into Re plus H plus minus G me m by Re plus H equals to G me m by Re plus H into 1 by 2 minus 1 equals to minus G me m by 2 into Re plus H. Required by a satellite. The, now the binding energy. The energy The energy required by a satellite to free it from the bondage of Earth and escape it to the infinity is called binding energy. The total energy of a satellite is minus G MEM by 2R, where R equals to RE plus H. In order to escape to infinity, it must be supplied an extra energy equal to G ME M by 2R so that its total energy becomes equal to 0. Hence, binding energy of a satellite is binding energy of satellite equals to GMEM by 2R, where R equals to RE plus H, and H is the distance of satellite from height of satellite from Earth surface. Geostationary satellite GSS, a satellite which appears stationary to an observer on Earth's surface is called geostationary satellite. Necessary condition for a GSS. First, the orbital plane of the GSS must lie in the equatorial plane of the Earth. Second, its sense of rotation should be same as that of the Earth, that is from west to east. 3. Its period of revolution around Earth will equal to that of the period of rotation of the Earth about its axis, that is 24 hours. Then if satellite fulfill these three conditions, then the satellite will be called geostationary satellite, that it looks stationary from the earth uh, from the earth. This is the orbital velocity of satellite at a height h r equal to re plus h. Now height of GSS, geostationary satellite. The time period of revolution of GSS is given by t equals to 2 pi under root re plus s to the power whole cube divided by g re square. This implies t square equals to 4 pi r square re plus s to the power whole cube divided by g re square. This implies t square g re square by 4 pi r square equals to re plus s to the power whole cube. This implies t square re square g by 4 pi square to the power 1 by 3 re plus h. This implies h equals to t square re square g by 4 pi r square to the power 1 by 3 minus re. Equation 1. Using t equal to 24 hours, 24 into 60 into 60 seconds, and re equal to 6400 into 10 to the power 3 meter, pi equals to 3.14 and g equal to 9.81. We get h equals to 35,920 into 10 to the power 3 meter, about 36,000 kilometer. And orbital radius r equal to re plus s, 6400 plus 35,920 equals to 42,320 equal to 42,000 kilometer. And this type of satellite is used in telecommunication and broadcasting etc. Now polar satellite. A satellite whose orbital plane is perpendicular to the equatorial plane of the Earth is called polar satellite. A polar orbit passes over north and south poles of the Earth and has a height of 500 to 800 kilometers. The polar satellite successively passes across the different parts of Earth's surface as the Earth rotates about its axis. Thus, the polar satellite can photograph entire surface of the Earth. This is shown the situation of polar satellite. This is equatorial plane, that is a plane passing through the equator, and this is north pole and this is south pole. So the satellite is revolving like this, and because Earth is revolving like this, so satellite will cover all part of the Earth. Time period of polar satellite is equal to about 100 minutes and h is 500 to 800 kilometer, and it is used in remote sensing, meteorology, environmental study etc. Now weightlessness in satellite. A body is said to be in a state of weightlessness when the reaction of the supporting surface is zero. For body in a satellite by Newton's second law, gme by r square minus n equals to ma equals to mv not square by r. Here this situation is shown because body is in the satellite, so weight is acting in downward direction and normal reaction is acting in upward direction. This is shown the free body of diagram r and mg, and because it is revolving in a circular path, so there must be a centripetal force also. So by Newton's second law we can write gme m by r square. This is the gravitational force minus n, that is minus m minus normal reaction, equals to m mass into acceleration, equals to m into v naught square by r, where r equals to re plus h and v naught equals to orbital velocity. This implies gme m by r minus n equals to m into under root gme by r to the power whole square. This implies gme m by r minus n equals to mgme by r. This implies n equals to 0. As no reaction force is experienced by the body, so body will experience weightlessness.